In 1951, Michelin walked into the Paris metro with an idea that sounded impossible: put rubber tires on the trains. Every subway on Earth ran on steel wheels back then, so rubber seemed like a dangerous gimmick. But today, Paris, Montreal, and Mexico City move millions of passengers a day on rubber-tired metros. They are quieter, faster, and can climb hills steel wheels can't touch. The trick is a hidden dual-wheel system under the floor that most riders never notice. And when you see how the concrete tracks physically slide to switch trains, you'll understand why this isn't a strange experiment. It's a deliberate engineering choice. We tend to picture a subway train the same way every time: a heavy metal car perched on steel wheels, grinding along steel rails. That image is so familiar that anything else feels completely wrong. That picture is changing. So when you hear that subway networks run on rubber tires instead of steel wheels, your first thought is that someone made a mistake. Rubber tires flatten under heavy weight, wear out faster than steel, and slip when it rains. On a multi-ton train, those problems sound catastrophic. But this isn't a mistake. Paris runs several lines on rubber tires, and Montreal built its entire metro that way in 1966. Mexico City runs more rubber-tired lines than any other city on Earth. These aren't airport shuttles. They're full-sized metro trains carrying hundreds of people. They run at full speed through long underground tunnels that were never designed for anything but the grinding sound of steel on steel. Forget whether it works. Engineers solved the problems that make rubber tires sound like a terrible idea, and they made the trade-off worth it. The real mystery isn't why someone tried it once. It's why 3 major cities built their transit futures around a technology that sounds like it should fail. And the answer sits under the car. To understand how this works, we need to look under the floor. What you see isn't a simple bus wheel bolted to a train. Each bogie carries large rubber tires that roll on a dedicated concrete rollway inside a steel or concrete guide bar. Those rubber tires carry the full weight of the car. But the engineers didn't stop there. The rubber tires aren't car tires. They're thick, reinforced rings built to carry massive loads at high speed. The concrete rollway they ride on forms a shallow channel, so the tire sits in a fixed path without a flange gripping it. Sitting just millimeters above a traditional steel rail, there's a second set of flanged steel wheels. They never touch the rail during normal operation. They sit in silence, waiting. If a rubber tire blows out or loses pressure at speed, the steel wheels drop onto the backup rail instantly, and the train stays on the rails. It doesn't even slow down in a dangerous way. The steel wheels take over, and the train can stop safely at the next station. That redundancy is the core of the system. The backup wheels aren't decorative. They're full-sized steel rail wheels with flanges, mounted on the same axle assemblies as the rubber tires. In normal running, they spin freely, millimeters above the surface. Horizontal guide wheels or bars press against the side of the guide rails to hold the train in the middle. Without them, the rubber tires would slide sideways on the concrete. The guide system does the job that the shape of a steel rail normally does. Some systems use small horizontal rubber tires as guide wheels. Others use steel bars that slide along the side of the concrete track. Either way, the principle is the same. The train is steered by contact with the walls of the guideway, not by the rail itself. So the train is actually running on 2 completely different systems at once. The rubber tires handle acceleration, braking, and everyday load. The steel wheels act as an insurance policy you hope never to use. And the guide bars keep the whole thing pointed in the right direction. This is why the idea isn't reckless or over-engineered by accident, and the backup isn't an afterthought. It's built into the same bogie, inches from the primary system. But the dual-wheel bogie only explains the safety side. It doesn't explain why engineers went through all this trouble in the first place. Now that we know how the train stays on track, the next question is why anyone bothered. Steel wheels on steel rails are simple, proven, and cheap to maintain. No one would complicate that without a real payoff. The payoff is performance in a tight urban space. Rubber on concrete runs quieter than steel on steel. In a dense city, where tunnels run under apartments and offices, that matters. Less noise means less soundproofing and fewer complaints. Rubber also grips better. That means faster acceleration out of a station and shorter braking distances when the train has to stop. In practice, a rubber-tired metro can run more trains per hour on the same track. That's because each train spends less time getting up to speed and slowing down. The biggest advantage is slope, because a conventional steel train struggles on anything steeper than about 4%. Rubber-tired metros can climb gradients of roughly 13%. That opens up routes through hilly terrain that would be impossible for traditional rail. That's the difference between a train that can climb a city hill and one that needs a tunnel bored straight through the rock. Rubber also absorbs vibration better than steel. In places like Mexico City, where the ground is geologically unstable, that reduced vibration protects the trackbed and the buildings above. But every benefit has a cost. The rolling resistance of rubber on concrete is higher than a steel rail system. That means the trains use more energy to move the same distance. They measure the resistance at roughly 0.01 to 0.02 for rubber on concrete, compared to about 0.002 for steel on rails, so the train has to work harder. Tires wear out faster than steel, and a steel wheel can last for decades, but rubber tires on a metro need regular replacement. All the extra friction from the rubber ends up as heat in the tunnel, and ventilation systems have to handle it. Because the whole system is bespoke, you can't just connect a rubber-tired line to a regular freight rail or a national network. It lives in its own world. Montreal's answer to winter is heated guideways. When snow and ice build up, the concrete track warms up to keep the trains moving. That adds complexity and energy cost. The real choice is rubber plus steel, plus guide bars, plus heated tracks, plus bigger ventilation, in exchange for speed, quiet, and the ability to climb hills. If the train doesn't run on steel rails, then switching from one line to another can't work the normal way. On a traditional railway, a turnout moves a piece of steel rail sideways so the wheels follow a different path. The flange on the steel wheel does the steering. But a rubber-tired train doesn't rely on a flange. It relies on guide bars pressing against the sides of the concrete track. So engineers had to rethink the switch entirely. With no flanged wheel to catch a moving rail, the train has no way to follow a curved steel path. On a rubber-tired metro, the concrete guideway itself moves. A section of track physically slides sideways to align with the route the train needs to take. It's a massive piece of infrastructure, and it has to shift precisely every time a train approaches a junction. There's no small steel rail clicking into place, just a whole slab of concrete, sometimes several meters long, shifting on rollers or hydraulic actuators. The tolerances are tight. A misalignment of just a few millimeters would force the operator to stop the line and fix it before the next train arrives. If the alignment is off by even a small amount, the guide bars won't seat properly and the train can't pass. That means every switch, every crossover, and every junction in the network is custom built for this specific technology. You can't buy an off-the-shelf switch from a regular rail supplier. You have to design, build, and maintain every piece yourself. This is one reason rubber-tired metros are usually found in closed systems like city metros. Every inch of track is purpose-built, and the trains never leave the network. So where does this actually win, and where does it fail? Paris was the first. In the 1950s, Michelin and the Paris transport operator RATP developed the system together. The first prototype, called the MP51, proved the concept. Today, Paris Line 14 runs driverless rubber-tired trains through the heart of the city. Montreal went all in. The entire network, opened in 1966, uses rubber tires. The city wanted quiet tunnels and the power to handle steep grades under the streets, and the system has run that way ever since. Mexico City built the largest rubber-tired network in the world. 12 lines run on the system, partly because the soft ground and unstable geology make vibration control essential. But there are places where rubber tires don't work. Heavy snow and ice can paralyze the system unless you heat the guideways, which Montreal does at considerable cost. In very hot tunnels, the heat from the tires adds to an already difficult cooling problem. Because the infrastructure is entirely custom, expanding the network or connecting to regional rail is far more expensive than adding a standard steel line. This system is a specialized tool for specific problems: noise, steep hills, vibration, and the need to squeeze more trains through an existing tunnel. It's not a universal upgrade. That hidden dual-wheel bogie is the physical proof of an engineering mindset riders never consider. Rubber handles the daily load, steel waits in reserve, and the concrete track moves when the city needs to change direction. If you want to see more of how the world works, hit subscribe.